Here's our first question. Do you know about the Kahn Academy online videos, and what do you think about using them as a supplement in a classroom?
How many people heard of? This is a medium that actually Larry and I have discussed. The idea is very good, that to make things available to everybody, I guess for free, right?
Mm-hmm. Yeah.
And there were snippets and so on. I haven't looked at it well enough, but I've looked at a few. And I think the format is good. I also think that the quality of the mathematics could be higher. And I think that's actually, Larry, am I right, that we try to do something about that? That we want to do something similar but of a higher mathematical quality.
Oh, nice.
That's the idea. This is Larry's call. I can do things like that. Larry can do it. Larry can do it.
Well,
I think that's what you're doing now.
All we have to do is chop it like for stir fry.
That's what you're doing now. See? That's it.
Trust them in little bits. Good titles.
How exactly did the Romans multiply 2-digit or larger times 2-digit or larger numbers? Did they just get so far, then use addition to complete the problem? How about division and adding greater numbers?
To my knowledge, the Romans actually did not do arithmetic with their numerals. They had a separate set of computational numerals. And that, exactly what that is, I don't quite know. But I know that they have something called something similar to the abacus. And so they basically, they knew that it was too complicated. And they had some ad hoc method of doing computation. They could have survived with computing with that, but that won't be numeral.
This is our last question for today. I would be interested to learn more about when zero and negative numbers were introduced and why negative numbers are not part of these conversations, or at least on the number line early on.
Well, there are two ways to approach negative numbers. One is, which is the standard one in the schools, I think, the one where we're doing it. We do whole numbers and do fractions, and then reflect the whole thing on the other side of the number line and do all negative numbers all at once. The other way, which is perfectly legitimate, is to do whole numbers, and then reflect the whole numbers to the other side, and then you get integers. And so you carry on integers with you all through the discussion until you're done with fractions, and then you do negative numbers, negative fractions all at once. Both are okay. There's no preference. The only thing about, I think some books actually introduce integers very early. The pros and cons for that is it gives you an advantage in introducing young children to negative quantity. For example, you're living in Minnesota, then you would have no negative numbers since day one, right? Because every winter is minus 53. Most of the time, right? But the problem with that is you introduce negative numbers, and you only use it as a language because you don't. You can add negative numbers. But even when you come to adding negative numbers with positive numbers, then you have to do quite a bit of explanation. And at that age, you probably do it by rote because it's probably too early to explain all those things. So you introduce something like this just for the sake of introducing a new vocabulary, basically. And sometimes it may lead to a certain mindset of learning it by rote, and that's okay. So that may be the one thing you worry about, because you don't do any mathematics with it until 5th or 6th grade, because multiplication is obviously complicated. So there's some people who say, well, why do you bother with such an early introduction when all you do is just look at it, use it to express some facts in, I don't know, today is -13, and other than that, then you don't do much with it, and you a little bit of a mathematical waste. We do what we do here just because this is one standard way of doing it. Take care of all the positive quantities completely, and then we don't worry about negative quantities. And that's fine. There's nothing wrong with it. So it's depends on what your preference is. And then when he said earlier today, or maybe yesterday, or today, yeah. So if you, a lot of you had some other questions, and some we probably decided that the answer should be given privately rather than open because maybe not everybody's interested in it. So if you have had a question for us and we didn't answer it, just approach me and Winnie, and we'll try to answer it. Okay. Are there other questions before you proceed? Okay, we're going to do addition algorithm. Now, I was hoping to do addition and subtraction algorithms, and the way things are going, I didn't expect this all morning on basically review. Was it? Not quite review, but topics we introduced yesterday. Yeah? So now we're a little bit behind, so we might have to eliminate some of the more assignments. We'll see. So I'll start with addition algorithm, and I hope to get most of the subtraction algorithm done. So addition algorithm. Suppose I want to you build each house, you tell students, well, the way you do it is very simple. Line them up. And then go column by column. 1 plus 5 is 6. 2 plus 7 is 9. That's the answer. What else do you want to know? What? What? 5?
But you're not adding a 2 and a 7.
That's 9. Oh, you mean? Oh, but that's the algorithm. So I tell you, that can be done. Any objections? Now that, well, in a sense, this is the real algorithm. Meaning that, as I explained earlier, the whole point of all these algorithms is that no matter how much you want to add. So, of course, if you think this doesn't quite display the power of the algorithm, think about it. Now, this is addressing to you, not to kids. Right? So, I'm trying to tell you that. 3, 4, 5, 1, 7, 2. 5-digit, 2 5-digit numbers. We're talking about 75,325 and then 21,470. What's on? Well, not a problem. Do a few more single-digit additions. 7. That's the answer. You should be impressed. Did in 10 seconds flat. But what's wrong with this?
What happens if,
What?
what happens if he goes beyond 9?
Okay, that's one issue. But that's really not a big issue, contrary to what you're told. That's not a big issue. I'll explain that later, but yes, we have to take care of little things like this. Right? For example, what if this is 5? Right? Suppose it were a 6. then 7 times plus 6 is 13, and then you cannot say 13, right? It looks like shape. Because single digit operation, you maintain the number of digits. So then you say, well, there's a little glitch in this procedure. We'll take care of that. I'll teach you that too, right? So when you see the 3, then you put the extra to the other side, and then it becomes an 8. No matter what, you can see the power of the. Well, teach that way. What's wrong? There's an obvious thing, right? You say, well, why is this 2? Right? But more important is the fact that what are you telling students? What are they doing? What are they doing? So what are you doing? What are you trying to do? Yeah?
So are you trying to find out how far along the number line it is from starting at 75,365 and going all the way 21,471 more steps?
That's one way to put it. Right? Do you see any books explaining why you have to learn it?
No.
Does any of your books say, here is something wonderful? And the reason it's wonderful is, what is so wonderful about it? Well, I'm going to copy this homework here. Let's do something. Go back to my original thing, right? That's why I told you that is 25, right? So this is you teach this first grade or second grade. So you teach this. How do you convince the kiddies to do this? What do you tell them? What they're doing? Yes?
Well, I would say that in the second column that they're doing 2 10s plus 7 10s.
Yes. Yes. All right. Yes, that's true. But still, my question is, why would they feel any need to learn this? Yeah.
So they don't have to count it all.
Well, okay. Do you think this is the common practice that you explain to children why they should bother with it? Was there any emphasis at all in the curriculum, in the textbook that you are furnishing? Is there an effort to sell this in that particular way? That it is a worthwhile skill to acquire because what? Well, if I were you, I would teach in kindergarten or one first grade, second grade. I'll tell them 35 plus 71. Find out what it is. Right? Now they have to know what it means to say 25 plus 71. What is it? What does it mean? What does it mean? What does it mean? Count, right? Count 71 steps from 25. So what are the chances that a first grader or second grader will get it right? Of course, put 71 on purpose. I didn't say 71 plus 25. I said 25 plus 71. You let them count. Wait an hour or two. Let them count. Let them make mistakes. I think all of them will probably make mistakes. They do straight. It's very hard. Their attention span is so small, so short. They all made all the mistakes, and then you show them, look, you don't have to waste time. There's a simple way to do it. Because, no, of course, you have taught them already how to add single digit number. Now they come back to the same issue. Right? Why do you make them memorize the multiplication table? Why do you make them memorize the addition table? So-called addition facts, or whatever they call those. Because then you put them to use and say, well, you remember how to add 1 to 5? Yeah, that's the same. How to add 2 to 7? Well, that's a 9. There it is. You don't believe it? Now you go back and check carefully, see if you don't get this right. This correct answer. But you have, as I've been trying to tell you, if you want to make them work, at least get them to understand that it's worthwhile. But textbooks did exactly what I did a minute ago. We have add, good, write it down, do numerical addition, that's the answer. I'll do another example for you. Do that. And now you get it? Okay, good. Now, here are 10 problems. All of you sit there and do it. Right? That's what textbooks try to make you do. And that's totally pointless. Because why should they learn it? So I suggest that you make sure that you, this is why, that's the other thing I emphasize, right? Whatever you do, never mind how you do it, make sure you explain what it is that you're doing. You are talking about very elaborate continual counting, right? The other one that I put up a minute ago, 5 digits, that's even unthinkable. Right? Nobody can count like that. So you tell them, no, you don't need to do any of that. Everything is reduced to single-digit operation. You can do now. So you make them. See, you're buying yourself a lot of credit by doing this. You make them memorize those single-digit addition facts. Put them to use and tell them, see, I told you. Right? It's worthwhile. You memorize that, now you put it to use. You make yourself, do yourself a favor. So that's the whole purpose. Now, so you convince them that it's worth learning. Then after that, the second duty that you have, is to not only tell them how to do something, but why what you're doing is actually correct. For young kids, that's I think. Well, for young kids, that's first grade, you don't use such big numbers. It drives them crazy. Maybe 25 and 11 or something like that. That's good enough. But you can illustrate this by, I would suggest, are marbles allowed in California country? Marbles?
Marbles?
Yeah. You don't worry about them putting them in their mouth.
No, we don't allow that.
Huh?
We don't allow.
Really?
They're gambling because they use them.
Really?
Mm-hmm.
Beans, count.
Beans, what? Beans, okay, count.
Beans.
We use
But,
we don't.
so I think you can give them 25 counters. Give them, what, 11 counters. You say, let them count first and say 25, 11, right? And say, now put it together. And say, now how many are there here? You have to count all over. But that's exactly what continuous counting is, right? Count to 25, count 9 more. That's counting. And as I said, the whole point is to make them see that you just do brutal counting. It is hopeless game. They know. Then you tell them. Now, so of course, you as we talked about yesterday. All 4 algorithms were part of the design of the Hindu-Arabic numeral system. Remember we talked about yesterday? Restricting yourself to only 10 symbols, using precision to continue counting. For all that, why bother? Well, that's exactly why bother. We set that up to make this possible. And of course, not to say those words to them, but you tell them, actually, these numerals don't come like 25 stragglers and 11 stragglers and lump them together. It's not like that, because they come in bundles, right? You know the tubes of pennies and what do you call them? Rows. They actually, the counters come bundled up like this. 20 is, you remind the place value. The 2 is 20. They know that. I mean, you just explain it, right? So it's 2 bundles of 10s. That is 5 factors. Oh, I don't mind using 7. So you have 7 bundles. So get that here, right? 7. And then 1 extra. If those 2 collections of counters come like that, then how would they come? They would figure it out. They would figure it out. If they don't, help them a little bit, make them believe they have figured it out. Right? And that's what it is, right? That's exactly what it is. Seven plus 2, 9 bundles. 5 plus 1, 6 factors. And that's what you call 96. That's the exact and precise explanation of this particular addition problem. So the whole point of the Indo-Arabic numeral system is that they're all prepackaged. If you're 3 digits, then some come pre-bundled as 100 rows, or whatever you call those. And then you just bundle up the 100 the rows of 100 separately, and then counting is very simple. Now, but we don't want to talk like that. I was just illustrating. We want to be able to see. This is why some believe that the best way to teach teachers is to teach exactly the way it's done in classroom. I don't agree with that assessment. I think we're adults, we can speak adult language, we can talk adult language, and we can come to an understanding that's a little bit deeper than what you can do in the classroom. So the more you understand it, the better you can do variations on your own theme. That's the idea. So I suggest that let's approach it as adults. We know how to write things down. So let's do that. So what's the correct explanation of this? Never mind children's classroom, but among us, right? 25 and 71. What is it? 25 we know perfectly. The exact form, remember? And 25.
Mm-hmm.
71. That's what the expanded form is good for. Mm-hmm. The expanded form of number is the key that unlocks all the algorithms. You see. Now I'm adding 4 numbers. And now you go back to what we call 2.1. You add any number, collection of numbers, you can add any which way you want. So given a choice then, 2 bundles and 7 bundles. You collect the bundles. Correct? Well, again, among adults, I hope I will at that level. I want to add this to this. I can skip a step, can I not? Because what? When you see this added to this, what comes to mind right away?
9 times 10.
Because of what? Distributive law. Right? Now, if it's still not second nature to you, that's okay. But just keep in mind that we'll be doing this all day long. So after a while, you'll have to be used to it. Right? So this is 2 plus 7. Plus 5. But that is exactly column by column addition. Single digits only. That's it. Now, don't forget that theme. Everything comes down to single digit operator. Nothing more, nothing less. Now, so you have many digits, you write more without increasing your understanding. So I think we can do without that, right? You can write. So that means it's very impressive. Add two 10-digit numbers, and in a matter of seconds, you get the answer, right? You bypass all that counting. But don't forget, by design, you achieve such simplicity because from the very beginning you control the development of the whole numeral system. You limited yourself to 10 digits. Why? Because that makes it possible. Now, as I said, this really is the whole essence of the addition algorithm. And it was mentioned, I think, somewhere. Well, of course, not the whole thing. I know it's not the whole thing. But the additional thing called carrying, you should really regard it as a sideshow. It's not the main point. Compared with this overriding fact that what it does is reduce any kind of addition to single-digit addition. That is the main driving force behind this whole algorithm. You understand that, and you know, you come to carrying, well, yes, it's a little obstacle, a little bump we have to overcome, but it's not a big deal. The big deal really is that the drastic simplification of the act of addition. So no matter how many digits, all I ever consider is single digits. That is the first thing that they have to keep in mind. Don't distract them with carrying and all that. That is auxiliary. Sideshow. Now, so let's handle that issue. So suppose let's increase the numbers to make it big. So I have to add. Now there's no question we're still doing single digit addition. The only difference is that now I have one number is visualized as 8 bundles of 10 and 5 stragglers. The other number is visualized as 7 bundles of 10 and 6 stragglers, right? You want to add, that means counting, right? That means counting. And the counting is obviously best done by count the number of bundles. Then count the number of stragglers. Right, that's it. Now what do you do? You have 5 and 6 stragglers. They make 11. But you know that the minute you have 10, you can bundle it up. Right? So this is and a straggler. 11, huh? Right? Here you should do single digit addition, 8 and 7. Well, of course, here now you have all together. Now 8 plus 7 is 15. The children know that, right? So 15, you have 15 bundles. So now you ask them, how many do you have? Well, they can tell you. It's 15 bundles of 10, one more, so 16 bundles of 10, and then one straggler. Now 16 bundles of 10, that they should also know. 10 bundles of 10 is 100. 16 bundles means what? 16 bundles of 10 means, so you have this bundle 100 and this plus this, so that would be what I'm going to do is to make it impossible for you to write down. So yeah, I should do better. So I should write this one, right? So you will have 15 bundles of 10 and 1 bundle of 10 and 1 step. Right? That's what we have. So that would be 16 bundles of 10. And 1 stack. And then 16 bundles of 10 is nothing but 1 bundle of 100. And 5 and 6 bundles. Okay. And 1 stack. Now this, you don't need to explain. I mean, any kid will recognize this is correct. Right? You can count. Of course, then you teach them to how to write it properly and register what they have done. So then it becomes what the usual thing. It's 11. Now, I understand that the American custom is put the 1 over here, and I suggest that you don't do it. Do it underneath. 11. Then here's 87 plus 1, which is the 16. So 16. But the 16 bundle is 1 bundle of 100 plus 6 bundles of 10. So that's 1 bundle of 100. That's a 100th place. What did I say? 6? Yeah, 6. Then, of course, that's only one of 106. Now, again, let's do it the normal way. Normal way. There's no difference. This is exactly the same. Right? So you say 85 plus 76. It's 88 times 10 plus 5 plus 7 times 10 plus 6. Again, we do the obvious thing, which is distributive law. 8 plus 7 also would be, 8 plus 7. Plus 5 plus 6. And this is the statement that everything is reduced to single digit column by column addition. Right? Now, you want to do the, now again, I hope I can skip some steps because you know this, I hope, yeah. 5 plus 6 is 11, so 11 is 10 plus 1. 10 plus 1, right? But, as I said, among friends, not with enemies, I can afford to say, the one left behind, but let the extra 10 join force with this group.
That's 8 plus 8?
No, not 8 plus 8, but it's 8 plus 7 plus 1. Why?
Oh, okay.
Because this is 1.
Yeah.
8 plus 7 is 1. That is 1.
Yeah.
And now you recognize, at this point you can simplify, right? This is 16 of those things. 16 of those things is 10 tens and 6 tens. So it's equal to 10 tens and 6 tens. And then by the distributive, now you backward distribute, no? I mean, this is straightforward. The other one was the backward. This is straightforward. That is 10 times 10, which is 100. So that's 1 times 10 squared, right? 10 times 10 is 10 squared. We're using the definition of the notation, exponential notation, right? Plus 6 times 10 plus 1. Yeah?
So I'm sorry, but going from this 10 plus 6 times 10 in parentheses plus 1 over to the 1 times 10 squared plus 6 times 10.
That's distributive law. What? This
I
is
look
what?
at the distributive law and I see 10 squared plus 60. That's what I see.
No. I mean, look. 10 plus 6 times 10. What does the distributive law tell you? Is what? 10 times 10, what? Plus 6 times 10.
Yes.
And that's why I wrote that.
Yes.
So I'm sorry,
Oh.
I misunderstood you.
Yeah, no, it's just the 1 times 10 squared. Why did you put in the 1 rather than just 10 squared? Because you wanted to.
There's 1 there, right? The 1 is always there.
One is the coefficient.
But that's what how you enter.
I see. So this is sort
You
of
want to
a
make explicit.
better explanation of the
Yes.
the hundreds place.
Not only that, it also reminds you how many copies of 100 you've got.
Yeah.
This is
Exactly.
good bookkeeping habit. Nothing more. So then let's stop for maybe a few seconds and see if this is the simplest of all of these. Okay. No question. Yeah? This really is this, as I said, really very simple. So go to page 65. The activity. So you have to practice on your nature.